Hello everyone, and welcome. I'm excited to kick off our presentation on gas turbine engines, starting with the inlet. Today, we'll explore the essential components and functions that make these engines work efficiently. Over the next slides, I'll guide you through the key concepts, and by the end, you'll have a clear understanding of how the inlet plays a crucial role in gas turbine performance. Let's get started. Let's take a closer look at the turbine engine operating principles, starting with the inlets and accessory air entrance. The main goal here is to efficiently conduct incoming air into the compressor while minimizing any energy loss. This means designing the inlet to reduce drag and avoid ram pressure loss, which can negatively impact performance. It's also crucial that the airflow into the compressor remains as smooth as possible, without turbulence. Turbulent air can reduce efficiency and cause uneven compression. So, a properly designed inlet not only helps maintain smooth airflow, but also enhances overall aircraft performance by increasing the ratio of compressor discharge pressure to duct inlet pressure. Finally, the amount of air passing through the engine depends primarily on three factors, with compressor speed, or RPM, being a key one. As the compressor spins faster, it pulls in more air, which is essential for generating the thrust needed for flight. All these elements work together to ensure the engine operates efficiently and reliably. Let's talk about turbine engine operating principles, starting with the inlet design. A high-bypass turbofan engine has an inlet that's quite different from what you'd see on a turboprop or turbo shaft engine. The key thing here is that the inlet on a turbofan is designed to handle a much larger volume of air, which is essential for high bypass ratios that improve efficiency. Most large gas turbine-powered aircraft are equipped with turbofan engines. These engines, as you know, are mounted on the wings or sometimes on nacelles attached to the aft fuselage. A few are even mounted in the vertical fin, especially on some specialized aircraft. The inlet itself is bolted directly to the front of the engine, forming a smooth, aerodynamic path for incoming air. This design helps maximize airflow into the core while minimizing drag and turbulence. Overall, the placement and design of the inlet are critical because they influence engine performance, fuel efficiency, and noise reduction, all of which tie back to the overall theme of optimizing aircraft propulsion systems. On this slide, we're diving into the operating principles of turbine engines, which are quite fascinating. First, you'll notice that warm air is bled from the engine's compressor and directed through the inlet. This process is essential to prevent ice from forming, which can be a serious issue at lower temperatures. If the engine uses inlet guide vanes to straighten the airflow, these vanes also have anti-icing air flowing through them. This dual function helps maintain smooth airflow and prevents ice buildup on critical components. You'll also see that the inlet contains sound-reducing materials. These materials are designed to absorb fan noise, making the engine quieter during operation, an important factor for passenger comfort and environmental regulations. For turboprops and turbo shafts, there's often an inlet screen. This screen acts as a filter to help block out ice or debris before they can enter the engine, protecting it from potential damage. Additionally, to further prevent ice entry, a deflector vane and a heated inlet lip are used. The deflector vane guides airflow effectively, while the heated inlet lip ensures that any ice attempting to enter is melted away before it can cause problems. All of these features work together to ensure the engine operates efficiently and safely, even in challenging weather conditions. On military aircraft, we often see a divided entrance design, which allows for the use of very short ducts. This design is crucial because it results in a smaller pressure drop due to skin friction, making the engine intake more efficient. Even though military aircraft are capable of flying at speeds above Mach 1, the airflow through the engine itself must always stay below Mach 1. Why is that? Because if the airflow inside the engine becomes supersonic, it would actually destroy the engine. To prevent this, engineers use specially shaped ducts, either convergent or divergent, to control and slow down the airflow before it reaches the engine. This is what we call a supersonic inlet. Its purpose is to slow the incoming air to subsonic speeds, ensuring the engine operates safely and efficiently. So, in essence, these inlet designs are critical for maintaining the right airflow conditions, especially when dealing with high-speed flight, and they tie directly into our broader theme of managing airflow for optimal engine performance. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the accessory drive section. This part of the system is responsible for powering several important components in the engine. It typically includes the belt, pulleys, and accessories such as the alternator, power steering pump, and air conditioning compressor. The key point here is that the accessory drive is crucial for the overall operation and efficiency of the engine. Without it, these accessories wouldn't function properly, which can impact vehicle performance and comfort. What's interesting is how this section connects to the overall theme of engine efficiency and reliability. Proper design and maintenance of the accessory drive help ensure smooth operation and prevent failures that could lead to costly repairs. So, understanding this section is essential for appreciating how all the engine parts work together seamlessly to power the vehicle and keep everything running optimally. Now, let's take a closer look at the accessory drive housing, or ADH for short. This component plays a crucial role in supporting the accessory drive system of the engine. Essentially, it houses the pulleys and belts that drive auxiliary components like the alternator, power steering pump, and air conditioning compressor. By keeping these parts secure and properly aligned, the ADH helps ensure smooth operation and reliability of the entire accessory system. Understanding the design and function of the ADH is important because it impacts the overall efficiency and maintenance of the engine. When we consider the overall theme of engine performance and durability, the ADH is a key element that contributes to these goals by providing a stable platform for accessory drive components. This slide doesn't contain enough information. That's why we're moving to the next slide. The accessory section of a gas turbine engine primarily serves as a dedicated space for mounting various accessories that are essential for the engine's operation and control. Think of it as the engine's control hub, where all the auxiliary components are organized and secured. These accessories include crucial aircraft systems like electric generators, which provide electrical power, and hydraulic pumps that help operate the aircraft's hydraulic systems. In addition to these primary functions, the accessory section also acts as an oil reservoir, or sump. This helps in oil storage and circulation, ensuring proper lubrication of engine components. It also houses the accessory drive gears and reduction gears, which are vital for transferring power from the engine to these accessories efficiently. The location of the accessory gearbox can vary depending on the engine type, but most turboprops and turboshaft engines have their accessory cases mounted towards the back section of the engine. This positioning helps optimize space and accessibility for maintenance. Despite differences in engine designs, the components within the accessory section across all gas turbine engines serve essentially the same purpose. They are crucial for providing power, lubrication, and control for the engine's operation, tying into the overall theme of engine reliability and efficiency. Now, let's take a closer look at the basic elements of the accessory section. First, we have the accessory case, which essentially serves as a mounting platform for engine-driven accessories. This case is crucial because it provides the support and structure needed for these components. Inside the accessory case, you'll find the gear train, which is housed securely and plays a vital role in transmitting power from the engine to various accessories. An important point to note is that the accessory case also acts as an oil reservoir. This means it stores the lubricating oil necessary to keep the gear train and supporting bearings running smoothly. To ensure proper lubrication, the accessory case is equipped with adequate tubing or cord passages. These passages are essential because they allow the oil to be sprayed or directed onto the gear train and bearings, reducing friction and preventing overheating. All these elements work together to ensure that the accessories operate efficiently and reliably, which is key to maintaining overall engine performance. Understanding these components helps us appreciate how the accessories section integrates into the engine's broader system, supporting both functionality and durability. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the gear train. This system is driven by the engine compressor through what we call an accessory drive shaft, or tower shaft. The shaft connects to a gear coupling that splines with both the gearbox gear and the compressor gear. Now, this setup allows the power generated by the engine to be effectively transferred to various accessories. Within the gear case, there's reduction gearing that adjusts the drive speeds to match what's needed for each accessory. This is crucial because different accessories require different operating speeds for optimal performance. Furthermore, these accessory drives are supported by ball bearings, which are assembled directly into the mounting pad bores of the accessory case. These bearings ensure smooth operation and stability of the drive components. Overall, this gear train is a key part of the engine's accessory drive system, ensuring everything runs efficiently and reliably, which is vital for the overall performance of the engine. Let's take a closer look at the accessory drive housing, or ADH. This component plays a crucial role in how the engine's accessory belt system is structured. Essentially, the ADH serves as the mounting point for various accessories like the alternator, power steering pump, and sometimes the air conditioning compressor. The design of the ADH is important because it ensures proper alignment and tension of the belt, which is vital for efficient operation and longevity of these accessories. If the housing is damaged or misaligned, it can lead to belt slippage or premature wear, affecting the overall performance of the vehicle. Connecting this to our broader discussion on engine reliability and maintenance, understanding the function and condition of the ADH helps us prevent unexpected failures. Regular inspection and maintenance of this part can save time and money down the road by avoiding more serious engine issues caused by accessory drive problems. So, in summary, the ADH isn't just a simple housing. It's a key component that supports the proper functioning of several vital engine accessories, contributing to the overall health and efficiency of the engine system. Today, I want to talk about the turbine engine inlet system. This is a critical component because it's responsible for directing the incoming air into the engine efficiently. The design of the inlet system plays a key role in ensuring the engine performs optimally across different flight conditions. It helps manage airflow, reduce aerodynamic losses, and prevent foreign object ingestion. A well-designed inlet system also minimizes turbulence and ensures smooth airflow, which is essential for maintaining engine stability and efficiency. As we see in the broader context of engine performance, the inlet system is the first stage in the power generation process, setting the foundation for everything that follows. So understanding its function and design principles is vital for appreciating how modern turbine engines operate reliably and effectively. This slide doesn't contain enough information. That's why we're moving to the next slide. The main function of an inlet duct is to supply the engine with the right amount of air needed for optimal performance. Many engines use inlet guide vanes, or IGVs, which play a crucial role in straightening the airflow and directing it smoothly into the first stage of the compressor. This is really important because uniform and steady airflow helps prevent compressor stall and keeps engine temperatures in check, especially in the turbine section. Usually, the air inlet duct is considered part of the airframe rather than the engine itself, but don't underestimate its importance. The duct is essential to the engine's overall performance, as it directly impacts the engine's ability to produce the right amount of thrust efficiently. So, in a way, the inlet duct acts as the gateway that ensures the engine operates smoothly and effectively. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Gas turbine engines consume more airflow than reciprocating engines, which is a key difference in their design and operation. Because of this, the air entrance passage for turbines is correspondingly larger to accommodate the increased airflow needed for efficient combustion and power generation. The size of the inlet actually varies depending on the type of turbine engine. For example, small turboprop and turboshaft engines tend to have a lower airflow requirement compared to larger turbofan engines, which need much higher airflow to produce the thrust required for commercial and military aircraft. You'll also notice that many turboprop, auxiliary power units, and turboshaft engines use screens over the inlet. These screens serve an important purpose. They help prevent foreign object damage, or FOD, which can be a serious risk to engine components. So, in essence, the design considerations around airflow and inlet size are crucial for engine performance, safety, and longevity, especially given the different sizes and applications of these turbine engines across various aircraft. As the aircraft speed increases, you'll notice that thrust tends to decrease slightly, which might seem counterintuitive at first. But what's really happening is that as air flows into the inlet at higher speeds, a lot of the pressure is actually lost due to various aerodynamic factors. However, as air molecules get trapped and compressed in the inlet, much of that pressure loss is recovered. This process is crucial because it means we're able to convert some of that kinetic energy back into pressure energy, effectively boosting the pressure at the engine inlet. This increase in pressure at the inlet is what we call ram recovery, or total pressure recovery. It's a key concept because it directly influences how much air is delivered to the engine's compressor. More pressure and airflow mean better engine performance. But it's not just about increasing pressure. It's also about ensuring that the inlet duct delivers this air smoothly to the compressor. The duct needs to do this uniformly, with minimal turbulence or pressure fluctuations, because any disturbances can affect engine efficiency and stability. So, maintaining a well-designed inlet duct that provides a steady, turbulence-free airflow is essential to harness the full benefits of ram recovery, especially as we push the aircraft to higher speeds. This is all part of optimizing engine performance and ensuring smooth operation across different flight conditions. When it comes to turbofan engines, one critical aspect is the duct design. The duct must have a sufficiently straight section to ensure a smooth, even airflow. This is especially important because of the high airflows involved, which can easily become turbulent or uneven if the duct isn't properly shaped. Now, the way we choose the configuration of the entrance to the duct depends on several factors. First, the location of the engine within the aircraft plays a big role. Whether it's mounted under the wing or on the fuselage can influence how the duct is designed. Second, we have to consider the airspeed. At higher speeds, airflow behaves differently, so the duct configuration needs to accommodate those conditions to maintain efficiency. And third, the altitude and attitude at which the aircraft is designed to operate are also key. These factors affect air density and pressure, which in turn influence airflow behavior and duct design choices. All these considerations are interconnected and are essential for optimizing engine performance and ensuring smooth airflow, which ultimately impacts the overall efficiency and safety of the aircraft. Now, let's take a closer look at the different types of inlet ducts. Inlet ducts are a critical component in any HVAC or ventilation system because they direct the airflow into the system efficiently. The type of duct used can significantly impact system performance and energy efficiency. There are several common types, each suited for different applications. For example, straight ducts are simple and straightforward, often used in long runs where space allows for smooth airflow. Then, we have tapered ducts, which gradually change in cross-sectional area to help control pressure and velocity. Another important type is the tapered inlet, designed to reduce turbulence and improve airflow into the system. Also, circular ducts are very common because they offer less resistance and are easier to clean and maintain compared to rectangular ducts. Understanding these different types helps us select the right inlet duct for each specific application, ensuring optimal performance and efficiency, which ties into our overall goal of designing effective and sustainable ventilation systems. Let's take a closer look at two important types of ducts, the divided entrance duct and the variable geometry duct. These are key concepts because they help us optimize airflow and improve system efficiency. Starting with the divided entrance duct, This design essentially splits the airflow at the entrance, which allows for better control and distribution of air to different parts of the system. It's particularly useful when we need to direct airflow precisely or manage pressure drops effectively. Now, moving on to the variable geometry duct, this is a more adaptable solution. It can change its shape or size depending on the operational needs. This flexibility helps us maintain optimal airflow conditions, especially in systems where demand fluctuates. Both of these duct types tie into the overall theme of designing efficient and adaptable air distribution systems. They showcase how engineering solutions can be tailored to improve performance and energy efficiency in HVAC applications. Let's talk about the divided entrance duct. This type of duct can be designed as either a wing root inlet or a scoop located on each side of the fuselage. The placement of these side scoops is actually quite strategic. They are positioned as far forward as possible. This allows the airflow to bend gradually toward the compressor inlet, which is crucial for maintaining good airflow characteristics. The goal here is to make the airflow as smooth and efficient as possible, closely resembling the airflow you'd get with a single entrance duct. To help with this, sometimes a series of turning vanes are installed inside the side scoop inlet. These vanes play a key role. They straighten the incoming airflow and help prevent turbulence, which can otherwise reduce engine performance. Overall, the design of divided entrance ducts, especially with features like forward placement and turning vanes, is all about optimizing airflow to ensure the engine operates smoothly and efficiently, fitting into the bigger picture of aerodynamic and engine performance optimization. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a look at the variable geometry duct. The main idea here is that the velocity of the airflow as it enters the air inlet duct needs to be reduced before it reaches the compressor. If the airflow is too fast, it can cause issues with compressor operation, so controlling its speed is crucial. Inlet ducts are essentially designed to act as diffusers. Their job is to decrease the velocity of the incoming air while simultaneously increasing its static pressure. This process ensures the air is at the right conditions for efficient compression. When we consider military supersonic aircraft, the diffuser's shape becomes even more critical. These diffusers are designed with a progressively decreasing cross-sectional area as the airflow moves downstream. This gradual narrowing helps manage the high-speed flow effectively. Once the airflow slows down to Mach 1, meaning it reaches sonic conditions, the design typically shifts. The supersonic inlet duct then features an aft section that actually increases in area. This part functions as a subsonic diffuser, further reducing the airflow velocity to subsonic speeds. This variable geometry approach is essential for maintaining optimal airflow conditions across different flight regimes. It allows the inlet to adapt dynamically, ensuring the compressor always receives air at the right pressure and speed, which is fundamental for engine performance and efficiency. When dealing with very high-speed aircraft, the airflow dynamics become quite complex. One important aspect is how the inlet duct, which guides air into the engine, needs to adapt as the aircraft's speed changes. Inside the duct, the configuration is actually altered by a mechanical device. This adjustment is necessary because as the speed increases or decreases, the airflow conditions change significantly. This leads us to what is called a variable geometry inlet duct. Essentially, it's a type of inlet that can change shape or size to optimize airflow efficiency across a range of speeds. By doing this, the inlet ensures that the engine receives the right amount of air, at the right pressure, regardless of how fast the aircraft is flying. This concept is crucial in high-speed aircraft because maintaining stable and efficient airflow is key to engine performance and safety. So, in summary, the variable geometry inlet duct is a clever mechanical solution that adapts to changing speeds, helping the aircraft operate smoothly at very high velocities. Now, let's take a closer look at the compressor inlet screen. Its main purpose is to prevent the engine from ingesting any foreign items that could cause damage. You can think of it as a protective barrier placed right across the air inlet. This screen helps keep debris, dust, or other objects from being drawn into the engine, which is crucial for maintaining engine health and performance. It's interesting to note that engines equipped with inlet screens, such as turboprops and auxiliary power units, are actually less vulnerable to foreign object damage, or FOD. This added layer of protection makes a significant difference, especially in environments where debris is more likely to be present. Overall, incorporating an inlet screen is a simple yet effective way to safeguard the engine, ensuring smoother operation and reducing maintenance issues caused by foreign objects. This aligns with our overall theme of engine protection and operational reliability. Let's talk about some of the advantages and disadvantages of inlet screens. One key point to remember is that screens do add to the inlet duct pressure loss, which can slightly reduce engine efficiency. While they serve an important protective role, they can also fail due to fatigue over time, especially after repeated cycles. It's crucial to understand that a failed screen can sometimes do more harm than good. If it breaks apart, debris can enter the engine and cause damage. That's why some aircraft are equipped with retractable inlet screens. These can be withdrawn after takeoff or whenever icing conditions are present. However, it's important to keep in mind that these retractable screens are mechanical components, and like any mechanical part, they are subject to failure. So, while they offer flexibility and protection, they also come with potential risks that need to be managed carefully. Overall, when considering inlet screens, we have to weigh their protective benefits against these operational considerations. When it comes to measuring intake conditions, the bell mouth compressor inlet plays a crucial role. Usually, you'll find this setup installed on an engine that's undergoing testing inside a test cell. Its primary purpose is to ensure accurate measurement of the air entering the engine. Generally, it's equipped with probes that measure both intake temperature and pressure, covering both total and static pressure readings. This helps us understand the actual conditions the engine is experiencing. The bell mouth itself is attached to the movable part of the test stand, so it moves in sync with the engine. This flexibility is essential for accurate testing, especially when the engine's position or orientation changes during the test. One important point to keep in mind is that as air passes through the screen or the bell mouth, there can be some efficiency loss. This means the air isn't passing through perfectly without any disturbance. So, if you're aiming for very precise engine data, you need to account for this potential loss in efficiency. Overall, the bell mouth inlet setup is vital for capturing accurate intake data, which is fundamental for engine testing and performance analysis. This slide doesn't contain enough information. That's why we're moving to the next slide. When it comes to turboprop engines, the air inlet presents unique challenges compared to other gas turbine engines. That's mainly because of the propeller drive shaft, which can cause airflow disturbances and complicate the inlet design. The inlet itself typically includes a hub and a spinner, which help streamline airflow and protect the engine from debris. Now, to prevent ice buildup on the inlet, especially in colder conditions, electrical anti-icing elements are often incorporated into the lip opening of the intake. This is crucial because ice can block airflow, reducing engine efficiency and safety. Sometimes, you'll also see a conical spinner used with turboprop and turbofan engines. This shape is beneficial because it prevents ice from accumulating on the surface, ensuring smoother airflow and safer operation. Finally, I want to highlight that the arrangement of the spinner and the inlet duct isn't just about aerodynamics. It plays a vital role in the overall operation and performance of the engine. A well-designed inlet system ensures optimal airflow, which is essential for the engine's efficiency, power output, and reliability. So, understanding these components and their functions helps us appreciate how critical inlet design is in the broader context of engine performance and safety. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the turbofan engine inlet section. High-bypass turbofan engines are typically built with the fan positioned at the very front of the compressor. The inlet cowl, which is bolted onto the front of the engine, plays a crucial role by providing a smooth airflow path into the engine. In engines that feature dual compressors or dual spools, the fan is actually integrated with the low-pressure compressor, which turns more slowly. This setup allows the fan blades to rotate at a lower tip speed, which is essential for achieving optimal fan efficiency. Another important point is how the fan helps protect the engine from foreign objects. When debris or other foreign material is ingested, much of it is thrown outward radially by the fan blades. Instead of traveling through the engine core, this material passes through the fan discharge, reducing the risk of damage to the engine itself. Overall, these design features work together to improve efficiency, safety, and durability of the engine, which are all vital for reliable aircraft operation. Now, let's talk about how warm bleed air is used in the engine inlet. This warm air is drawn from the engine itself and circulated along the inside of the inlet lip. Its main purpose is to prevent ice from forming on the inlet, which is crucial for maintaining safe and efficient engine operation. Moving on to the fan hub or spinner, it can either be heated by this warm air or, as mentioned earlier, it might have a conical shape to help with aerodynamics and cooling. And inside the inlet, you'll notice sound-reducing materials. These are specifically designed to lower the noise generated by the fan, helping us achieve quieter operation and reduce the environmental impact. All these features work together to ensure the engine runs smoothly, safely, and more quietly, fitting into the overall theme of efficient and safe engine design. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about the fan compressor, which is a crucial part of high-bypass engines. The fan typically consists of just one stage of rotating blades and stationary vanes. These blades can vary quite a bit in size, with diameters ranging from less than 84 inches up to more than 112 inches. The blades themselves are made from either hollow titanium or composite materials, which helps keep them lightweight yet strong enough to handle the stresses of operation. Now, an interesting aspect of these fans is how they generate thrust. The outer part of the fan blades accelerates air, creating a secondary airstream that's ducted overboard without passing through the core of the engine. This secondary airflow is responsible for about 80% of the thrust in high-bypass engines, which is a significant portion. Meanwhile, the air passing through the inner part of the fan blades becomes what we call the primary airstream, fueling the engine's core. Understanding this dual airflow process highlights how efficient and powerful modern jet engines are, especially those designed with high bypass ratios. It's a smart design that maximizes thrust while maintaining fuel efficiency, tying into the overall theme of engine innovation. Now, let's talk about how the air from the fan exhaust can be discharged. There are two main ways this can happen. The first is through short ducts, known as dual exhaust nozzles, which direct the air straight outside through openings located right behind the fan. This setup allows the exhaust to exit directly to the outside air. The second method involves a ducted fan, where all the airflow is channeled through closed ducts that run all the way to the rear of the engine. At the back, the airflow is expelled through what's called a mixed exhaust nozzle. This configuration, where the airflow is fully ducted, is what we call a ducted fan engine. An important point here is that, in a ducted fan, the core airflow, which passes through the engine core, and the fan airflow, which is generated by the fan itself, actually mix together in a common exhaust nozzle. Understanding these different exhaust methods is crucial because they directly impact engine efficiency, noise levels, and overall performance, which are key themes in our discussion of jet engine design. Thank you all for your attention today. I really appreciate your time and engagement. I hope the key points we've discussed have provided valuable insights and practical takeaways. Remember, the main goal is to apply these concepts effectively in your own work. If you have any questions or want to explore any topics further, please don't hesitate to reach out. Once again, thank you for being here and for your commitment to continuous learning. I look forward to seeing how you implement